Now, why are we doing all of this? We're supposed to be talking about ozone and oxygen, so we want to get back to that. Now we understand something about the mechanics of predicting the types of bonds that exist in these different covalent compounds. We looked at the Lewis structure already at the very beginning of oxygen, and we correctly predicted that that's the Lewis structure of oxygen. Oxygen has a double bond. Now let's look at the Lewis structure of ozone. Ozone is O3, okay? And so if you do the available electrons, it's in group 6, so it's 3 times 6 equals 18. The needed electrons, and obviously it's not special, it needs 8, so that's 24. So the number of bonds, we'll cut to the chase here, is going to be 24 n minus a, 18 divided by 2. That's what we always do for the bonds. So we're going to predict 3 bonds, okay? And so what you do is now go back to it, draw the skeletal structure. They all have to be connected by at least 1 bond, all right? And so that's, remember, 2, 4. I've used 4 electrons because each dash is a pair. Out of a total of available of 18 electrons, that's how much I have to work with. All right, so now I've got, I've used 4, I have 14 left, so I'm going to start placing them on what's considered the terminal. The outer ones, 2, 4, 6, 8, 10, wait a second, 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, and so when I place all of my electrons, I have satisfied the octet for what we would consider terminal in this case, 8 and 8. But if you look at the central oxygen, there's only 6. So I can take a terminal pair and move them and create a double bond there. All right. Who's to say to pick this one or this one? So we have an instance again where it doesn't matter, you know, which pair you pick, you're going to end up with the same structure. So we're going to have a resonance situation where we have, if I would have moved that one, okay, I'll just draw that one first. If I would have moved that one, it's going to look like this. Or the other extreme is moving the pair on the other side, and so that's going to be looking like this. Okay, and since they're both available at the extremes, I'm going to put them in brackets. That's indicating that I have resonance. And indeed, when the chemists take a close look at the ozone, this bond is not a single bond, and this bond is not a double bond, but really it's this case of resonance where it's somewhere in between. Each OO bond is about 1.5 bond strengths. Okay, it's not a single bond, it's not a double bond, it's in between. So, so it's not the same bond strength. In oxygen, we have a double bond, it's a strong bond. In ozone, we have a resonance situation. We don't have a double bond, we don't have a single bond, we have something in between the extremes. So the bond strength of ozone is less than oxygen, but not as low as a single bond. All right, now that is going to be important in understanding, and not only that, this molecule, and this I'm going to tell you, but you don't know why yet, but this molecule is actually sort of bent in structure. A lot of times people have seen the water molecule, and you know that water molecule is bent, that it kind of looks like Mickey Mouse ears or something. The same thing is true with this oxygen, ozone. If I look at the structure, it's kind of bent like that, okay? Whereas if I just look at the structure, don't worry about the bonding, just look at the structure. This is a little linear molecule, this is bent. Because we have the double bond, and because we have the somewhere in between single and double bond here, the bond energies are different. Also, the shapes are different. Okay, and based on the difference in shapes and the difference on bond energies, that's why we have different properties of ozone and oxygen. And it's not until we take a close look at it and we truly understand what all these dots and dashes and arrows and brackets mean that we can truly understand the difference between the chemical and the physical properties of ozone and oxygen. Okay, so this is what we know now. We know that the Lewis symbol for oxygen looks like this. It's a single oxygen atom, and it's got 6 electrons in its valence shell. All right, this is very unstable. We don't find oxygen atoms existing for very long in nature. This is the most stable form of elemental oxygen. It's a nice double bond. This is the Lewis structure. It's a nice stable molecule. It does react with other molecules, but it's stable enough to exist in our atmosphere. The ozone molecule, this is one extreme. Of course, it's somewhere in between a single and a double bond. It's a resonance structure with this, either on the double bond on this side or this side, but really it's somewhere in between. And that's the ozone molecule. The bond energies are of lower energy. And then one more Lewis structure that I want to point out to you is of the hydroxyl free radical. Notice this is not the hydroxyl or hydroxide anion. The hydroxide anion carries a -1 charge. The hydroxide anion looks like this, and the Lewis structure is like this. It's got one extra electron, which gives it that negative charge. The hydroxyl free radical, we can see it's got bonding pair of electrons, 2 non-bonding pair of electrons, and then this single unpaired electron. Single unpaired electrons are also very, very unstable and reactive, okay? So we have an unpaired electron here on the oxygen atom. We have an unpaired electron here on the hydroxyl free radical. And so these two characters are going to play into us understanding the importance of the ozone in the ozone layer in the stratosphere, and what we call ozone chemistry in the stratosphere. So I want to point out those Lewis structures. So once you have some clue about how the electrons are existing in these molecules using these are just models. Of course, electrons aren't dots for real, but it's a way to model the difference at a more detailed level between these various species.